Hello, everyone. In today's discussion, we are going to talk about the MOSFET switches, which is another semiconductor device in electrical engineering. Now, in our discussion, we are going to talk about, and we are going to assume PMOS MOSFET, but the NMOS MOSFET, which is another category of the MOSFETs, are going to be the same. The only difference is that the junction, the semiconductor N and P are reversed in place, and the direction of the current are also reversed in the switches. Now, let's begin. The MOSFET is three semiconductors connected to each other. The channel in the MOSFET for PMOS is a P semiconductor, and we have N semiconductor connected to the source, to a gate we call it source, and another gate we call it drain. Okay, between them we have another gate, another terminal that we call it gate, which is the control terminal in our MOSFET. Now, if we apply a voltage to the gate, okay, and the voltage exceeds a certain threshold, the channel here would be influenced by the electrical field, okay, here between like a gate and source, okay. And what's going to happen is that now this semiconductor get polarized, and now we have a channel that allows the charges to pass through between the source and drain. Okay, now the symbol that we use for a MOSFET in our circuit schematic is like this. Okay, this is the symbol for MOSFET. As you can see, we have three gates, three terminals, drain, source, and gate. Okay, in PMOS, current goes from drain to source. You can see the direction of the current here. And in NMOS, it's in reverse. So the direction of the current is going to be the other way. Okay. Now, as we said, if the threshold of the voltage between gate and source, if the voltage between gate and source exceeds a certain threshold, now the switch starts conducting, as we call it, is going to be turned on. Now, there is a relation between the voltage, which is the voltage between the drain and source, okay, and the current that passing through the this component, okay. If our voltage of gate and source, voltage between gate and source exceeds the threshold, the switch is on. If it's lower than threshold, the switch is off. So if our voltage, okay, if our voltage between gate and source, here voltage gate and source is lower than threshold voltage, this comes in an off curve. So it's zero. The voltage is zero, the current is zero. So it doesn't matter how much voltage you apply for DS, the current is zero. Okay? So you can apply like a 100 volt, 10 volt, 20 volt, doesn't matter between drain and source, still not conducting any current. When the voltage between gate and source is less than a voltage threshold, that is defined in a data sheet of a specific MOSFET. The model that we are working with. All models that have different type of different level of the voltage threshold. Now, as much as we can see, if we set the voltage between gate and source at a certain level, like VGS1, which is higher than the threshold voltage, now we start conducting current. Okay, so but if we increase the voltage between gate and source, okay, the level of the current that we can conduct would increase. Now, if you look at this physics of this component. It means if we have higher level of the voltage, but let's say we have VGS1, so the channel would be this much polarized. Okay, that's actually in reality is like that. Okay, now if we increase the voltage between gate and source, it's gonna increase and we have wider channel. Okay, so that means that when we here we have like a voltage between gate and source, the second voltage too, which is bigger than the first voltage gate and source that we have. Now this area is wider, so we will have more current. We have more capability of passing through current. And as you can see, as we increase the voltage between gate and source, the current, the value of the current would go higher and higher. Okay, now we said voltage gate and source bigger than threshold is on, voltage gate and source lower than threshold is off. Now, when you look at the characteristics, you can see that we have an exponential increase, it's kind of an exponential increase, but at a certain level, it's become constant current. Regardless of the voltage between drain and source, we have a constant current. As you can see, this mode is saturation mode. What that means? That means it doesn't matter how much voltage you apply between drain and source. When you exceed a certain level of voltage, the capacity of the channel that exists here, okay, have a maximum cap of the amount of charge that could pass through. So you are going to get to the maximum amount of charge capable of passing through this channel. And after that, if you even increase the voltage, you are not able to increase the amount of charges that passing through between the gate and source. So there is a saturation level. This is this area, okay, on the right side of our board. So this is where the channel is fully loaded, okay, and you cannot exceed the current anymore. Okay, so it's a saturation. Before that, as much as you apply, as much as you increase the voltage, okay, is like an open up. You are increasing the amount of charge because you are increasing the pressure applied to those charges. Okay, so you are increasing the amount of charges that going through that channel. So by increasing the voltage between drain and source, you are going to increase the current passing through that MOSFET. This region, we call it teriod mode. So this is teriod mode. This is saturation mode. Okay, now, as you can see, okay, the application that we can have for the MOSFET in the two regions are completely different. Okay, so here we have a line. That means we can use this line as a ratio. Okay, what that means? That means if we consider the voltage between drain and source as an input, okay, this ratio would create a multiplication of that input and give us the current, which is the output. So it's very simple that here, like for example, if you consider that a very simple line, approximate that curve with a simple line, okay, with a ratio of, with a slope of like alpha. Now your current is equal to alpha times the voltage ds. Okay, so it's work as an amplifier with the gain of alpha. Now, here, it doesn't matter how much you increase the voltage, the current is constant. So the current is equal to some constant beta. Okay, so what that means? That means in this region, we could basically, by controlling the VGS, we could turn on and turn off the MOSFET. Okay, so it's become a switch. In the saturation mode, it becomes a switch. Now, if we increase the VGS after we pass the threshold, we could increase the capability of our system to provide or consume more current. But the reality is like it's only switch on and off between the in the saturation mode is just like work as a switch on and off. There is no gain. Okay, so this is the overall IB characteristics of an MOSFET. Now, we all already talked about the voltage and current. Now, when we talk about the saturation mode, which is mostly where we are going to use these MOSFETs, okay, the MOSFET is normally used as a switch, not as an amplifier, okay? Because we are using mostly the MOSFET as a switch, we normally play in this area, in the saturation mode area. Okay, now you can see that the current is not the function of the voltage between the drain and source, but it's a function of the voltage between gate and source. Okay, so if you go through the physics of that, I'm not going to go through deep of the physics of this semiconductor component and the physical parameters inside this component. The current that passed through the switch, which we call it ID or I drain, okay, is a Kn coefficient. That Kn is a function of the physical characteristics of this MOSFET. So it's like the length, the material inside it, the distance between the two gates. There are a lot of parameters that contribute to create this Kn. But you don't need to worry about it. You can easily measure the Kn in the lab. And in a data sheet, there are information that you can have the Kn easily. Okay, so don't worry about what is inside the Kn. Now, we said it's a value is a function of the voltage between gate and source. Now, if you do the small signal and large signal evaluation and analysis of the gate of the MOSFET, you can find that the current passing through the drain is equal to Kn times the difference between the VGS and threshold voltage. All of that difference is squared. Okay, so if we increase the VGS, okay, as you can see in the graph, we have more current. If we decrease it, we don't have any current. Now, if VGS is less than voltage threshold, this is not the function that you want to use, because on that part, it's turned off, meaning the ID is 0. So when the VGS is lower than the voltage threshold, this is not the function to calculate, this is not the equation to calculate the current. The current on that area is 0. Now, if we exceed voltage threshold, now we can calculate the level of the ID, the level of the current, okay, in the saturation. Be careful. This is in the saturation, not triangle. In the saturation. Now, this is the theory behind the MOSFET. As we said, the difference between the PMOS and NMOS, all the things are similar. The only difference is that the type of the semiconductor in the component, like in the PMOS, these two are P, and this one is in NMOS, these two are P, and the channel is N semiconductor, and the direction of the current is reverse direction, like from source to drain. In an NMOS, the direction is from source to drain the current. In PMOS, it's from drain to source. Now, this is the theoretical concept that we need to talk about in our discussion for the MOSFET. Now, we are going to go through the exercise 1, and we are going to talk about the simulation and then the experiment that we have in the exercise 1. Thank you. Okay, now that we talked about the MOSFET has a semiconductor component, and we reviewed the theoretical part of MOSFET, let's talk about the simulation. Let's see what if we could like replicate that IV characteristics that we talked about in a simulation. Now, I already created the circuit. So we have a MOSFET, which is an NMOS, and for finding them, you can go to the place, option component. There is a transistor group. In the transistor, you can use the MOSFET N-type or P-type. We chose N, and here you can find the model that you want. We wanted to like work with the BS170. So this is how we could choose our MOSFET. The sources we added, one is between the drain and source, and another one is between the gate and source. And we have a resistor, so we could have a limited amount of current, but I add the resistor as 1 ohm, so I don't want to like change it a lot. Now, in order to simulate and have the IV characteristics, there is a tool in the multisim on some of the versions that actually have the IV characteristics tool. So if you go to the tools and you have the IV characteristics option in your tool menu, you can choose that and automatically create the IV characteristics. Now, if you don't have, like my version doesn't have that, so we have to like do that manually. So what to do is to add an amp meter, because we wanted to like measure the amp meter as the output of our measurement based on the voltage between V and source, drain and source. So we are going to go to the menu simulate, and we're going to choose analysis and simulation. Here, we wanted to like change the DC source, so we choose DC source. Now, we have 2 DC source. So originally, this check mark is not activated. Okay, so you have your source connected between the drain and source, V1, which I already put the value 20 volts. And we are going to ask the multisim to sweep the voltage from 0 to 20, and you can define the step. I put 1 volt, so it's good enough. You don't need to go lower than that. And another part was, okay, in this sweep voltage, we only get 1 pair of the characteristics, because the voltage between gate and source does not change. So those multiple curves that I showed you on the board, this is not going to happen here. To create that, you activate the second source. We already choose that. So it's V2. And I put the 10 volts, and I ask the simulation to sweep the voltage from 0 to 6 with the 2 volt step. Now, remember one thing. The BS170, the voltage threshold is around 2 volts. So before 2 volts, we expect to not having any current. So this is the off mode. Or as rigorously we call it the cutoff mode. Okay? But after that, you should start actually conducting current. Okay, so what we expect is that in a 0 and in a VGS equal to 2, we shouldn't have the current. And after that, at 2, it should start a little bit of current because we already reached the threshold. Okay. And in 4 and 6, we have to have a decent amount of current. Now, we have that. Let's save the setting and we click run. And as you can see here, the red line is the voltage equal to 0, and we have 0 amp. Okay, so it's the cutoff mode. Voltage equal to 2, it is actually the threshold. So you can see there is a little bit of leakage, but still very low, close to 0. When we exceed the voltage between gate and source to 4 volt, you can see that it starts conducting. Okay, and as the voltage between the drain and source increase, the current will increase until it's saturated and is constant. Same goes when we want to apply the volt between 6 volt between the gate and source, which as we can see, it would increase until it gets saturated as the voltage between drain and source increase. And you can clearly see, like this is the a border that we earlier showed on a board. So we have a triode mode and a saturation mode. Okay, so this is perfectly shows that, okay, our anticipation, theoretical anticipation, would be confirmed by the simulation in the multi-sim. Now, another simulation that we wanted to see is to see the current as a function of the voltage between gate and source. Okay, to do that, we need to go to the analysis and simulation menu, and we need to change the order of the voltage sweeps. Now, the first one is going to be V2. So this V2, which is the voltage between gate and source, is going to be our horizontal line. Okay. And we want to go from 0 to 10. Let's choose the step 2. And here in the voltage, we want to go from 0 to 20. Again, step 2 is good. Now we save it. This one should show us the relation between the current going through the switch to the MOSFET as a function of voltage between gate and source. If you remember that current, the equation was Kn, that coefficients, times the difference between the voltage gate between the gate and source and voltage threshold. So that means we have to do 2. The voltage between the gate source and threshold, that difference is a square, and then times Kn become the current. So that was the function. Okay, so what we expect is having a hyperbolic curve in our graph. Now let's see what's going to happen. Let's simulate. As you can see, let me sweep more voltages so it's more clear. I'm going to include more voltages. This one is good. This one is 10. Let's go one step. I hope this one helps to have a better. Okay. As you can see, it's not zoom out enough, so it's hard to actually visualize, but you can see that the curve between the current ID and VGS here, horizontal axis is VGS, vertical axis is current. Okay, as you can see, the formula, the curve is replicating very close to the hyperbolic, so it's like a square of VGS times a certain coefficient is going to be the current, VGS minus V threshold. Okay, so there is a deviation from that perfect, as you can see here, and here in the curve, there is a deviation from the perfect hyperbolic function. And this is because of two reasons. First of all, the equation that we had was a simplified version of the actual physical equation. Okay. And the second effect is that we chose a discrete kind of like simulation. So we are using like a 1 volt as a step. So that also create a little bit of deviation. So, but beside that, we can perfectly see that, okay, this curve also is consistent with what we expected as the function between, as the relation between the current and the voltage between the gate and source. Okay, let's go through the actual experiment in the lab. Okay, let's start with the actual experiment in the lab. Now, before we start, we need to talk about how we can okay, now let's start with the actual laboratory and measure what's happening in our circuit. As you can see, I already put the circuit based on our exercise schematic. Now, one thing to pay attention to is when we talk about the MOSFETs, okay, the MOSFETs had, as we said, three terminals. Now, when you hold a MOSFET, one of the side of the MOSFET is a flat surface, which the model is hacked on that, okay? Now, when that flat surface is in front of you, okay, the left pin is the drain, the right pin is the source, and the middle one is the gate. Okay, so when you wanted to like connect them, remember the flat surface should face you. Okay, then the left one is drain, the right one is source, and the middle one is gate. Now, since I didn't have a 1 ohm resistance, I used a potentiometer, and before I connected, I set it in 1 ohm. So we have the circuit. Now I have only one DC source. Okay, so I'm going to use that for the voltage between drain and source. And for the gate and source, I am going to use the function generator. Okay, and I am choosing a square wave. Okay, but the duty ratio I'm going to put to 100%. In reality, it cannot provide 100% ratio. Okay, so if you put 100%, it would automatically turn it to a 99.99%, which is close enough. Okay, and so this is going to be our circuit, and what I wanted to like measure is the current passing through the circuit, okay, versus the voltage between drain and source. Okay, now before I'm doing that characteristics, I want to measure what is the actual like voltage threshold. Okay, what is the threshold voltage that the switch is going to be turned on? Now, to do that, first I set the amplitude at like 1 volt. Okay, and it needs an offset. So when you say 1 volt, the function generator, this is 1 volt peak to peak. So the function generator would create a signal from -1, -half to +half. Okay, so you need a half of the voltage as an offset. So you have now from 0 to 1 volt. And when you have 100% duty ratio, it's basically a DC 1. So I am going to choose half volt of a DC. So now I have a DC 1 volt. Okay. And I'm going to apply that to the gate. And at the same time, I'm going to apply the 10 volts between drain and source. Now, as you can see, I am measuring the current, okay, by putting the multimeter in series with the drain and with the source and the ground. Okay, so you can see there is no current. It's almost zero. Okay, now I am gonna change the voltage to 1.5. Sorry. 1.5 peak to peak, and this means my offset is going to be 0.75 DC. Okay, now let's apply that. Okay, it's still no current. We are still with on 1.5 point. We still are below the voltage threshold. Now let's go to 2 volt. Amplitude 2 volt peak to peak, and the offset is going to be 1 volt DC. Okay, let's see what's going to happen. Now, if you see, it start to have some current. Okay, so you can see that by applying the 2 volt, now our MOSFET is turned on. Now, we want to see what is the curvature, okay, of our IV characteristics. Now, for that, because 2 is the threshold, I am going to apply higher voltage. So we have like 5 volt. So we have a proper, voltage between the gate and source. So if the 5 volt, that means we have 2.5 offset. Okay. Now I'm gonna change my DC source between the drain and source to 0. I am gonna apply the I am gonna apply the voltage to the gate. So now the switch is on, but there is no voltage in drain and source. So it shouldn't show any voltage, but it says minus something, which is error. Okay, so it is offset error or the leakage somewhere. Okay, so I am gonna start to increase it to the 1 volt. For 1 volt between drain and source, my measurement shows 5.08 milliamp. So I'm gonna write that down. Okay, so for 5 volt, so 1 volt DS, I have 5 milliamp, 5.08 milliamp. Okay, now I am gonna increase that to the 2 volt. For 2 volt, my ammeter shows 9.81 milliamp. So this is another point in our graph. Increasing to the 3. Oh, okay. In 3 volts, my ammeter shows 15.1 milliamp. So it's the third point, data point in our graph. I'm gonna move forward. In 4 volts, it shows 19.82. Okay, you can see the increase, the rate of increase already slowed down. Okay, now I am going to go. Remember, it's 19.8. I am going to 5 volts is 24.71 milliamp. 6 volt is 29.9930 milliamp. Okay. In 7, I see 34.5 milliamp. At 8 is 39.4. At 9 is 44.8. At 10 is 49.4. Now I'm gonna step up a little bit because I want to save some time. At 12 volt is 59 milliamp. Come on. At 15 is 74. At 20 is 99. Okay, my circuit is not gonna tolerate that much of a current, so it will start to have a problem. But as you can see, you can draw the graphs based on what we saw in our measuring point. Now let's go a little bit lower, so we have a lower amount of current. Okay, amplitude goes to the 2.1 and volt amp to amp. Offset means 1.05 DC. Okay, and now we are going to the 5 volt. It shows 0.7 milliamp. And in 10, it's 0.78. At 16 is 0.9. At 20 is 1. At 25 is 1.1. And 30 is 1.4. You can see it's slowed down a little bit, and this is the max. 31 is 1.5, so it's beginning to go toward the saturation. We can test a better see a better curvature if we change the amp meter. Okay, so we reach the if we change the resistor, so we reach the saturation current faster. Okay, but this is the gist of it. So this way you can measure the data points and graph your IV characteristics for different voltage between gate and source and different voltage between the drain and source. So this is for the exercise, this task of exercise 1. Oh, by the way, before I forget to tell you about that, we talked about the Kn, that coefficient in our system. Okay, so that Kn, if you remember, was the coefficient in our function, in our equation that relates the current to the voltage between the gate and source. Okay, now in order to measure that Kn, that function, that coefficients, okay, in that function, now you have a lot of data points that you already have, like different voltage between gate and source and different currents. Okay, so you can set the drain and source in a constant voltage and switch the voltage between gate and source. Okay, by that you have a series of data points, which basically we know the threshold is 2 volts. So you can calculate on paper what is the difference between the measured voltage of gain and source minus the threshold, which is 2 volt, okay? And you already have the current measured with your multimeter, okay? So that way, if you divide those with each other, so the square of that distance divided by the current that you measure, you have the Kn coefficients for this specific BJT. Now, if you measure different points of VGS and measure the current, so set different VGS and measure the current, the Kn that you would see for each of those samples are going to be slightly different. So what you can do is to average them out, okay, and find the mean value of those Kn and say, okay, the approximation is that mean value. So I'm going to consider the Kn equal to like alpha or beta, whatever you calculated based on your measurement. So this way, you can also measure that Kn based on your experimental set. Okay, hello everyone. In this part, we are going to talk about how we can build the logic circuit from the MOSFETs. We normally use the PMOS and NMOS and the combination of those MOSFETs, okay, which that combination we call it a CMOS, okay, a complementary MOSFET, okay. But today, in this session, I am going to go over the logic circuit, the four main logic circuit, and I'm going to use only the MOSFETs, the NMOS MOSFETs. Okay, so the logic circuit that we are going to talk about is one is the AND circuit, another one is the OR circuit, then NAND circuit, and here is the NOR circuit. Okay, now let's start with the NAND circuit. Now, as you can see, we put the two NMOS in series and we use the gates of each NMOS as the inputs for our logic. Okay, the both sides of the NMOSs, this series of NMOSs, are connected between the ground and the voltage source. Okay, and we have a resistor here in order to control and basically limit the current that pass through these components. Now, the indicator that we use to see the output of that are and control circuit, okay, the logic circuit, is the LED that we connected in series with those MOSFET block. Okay, so we can use that LED as an indicator of our logic circuit. Now, if you don't want to use the LED, like for example, you might want to like have the output as an electrical signal, not just as a light. Okay, then you can use, instead of the light for the LED, you can use the voltage across this resistor. Okay, so you can use the voltage across this resistor as the electrical signal instead of that LED. Now, let's walk through. We have four combination when we have two inputs, and we want to like talk about the AND. If we have, if both of them are on, both of them has one, okay, then the LED should be on. This is the AND circuit. If one of them is zero, okay, the AND would result in zero, which the LED should be off. And when both of them are zero, also it results in zero, so the LED should be off. Now, let's look at it. We have the voltage, okay? So when the LED would be light up, when you have a current passing through the whole circuit. So if we apply the voltage at the gate A, okay, and the gate B, that means both switches are now conducting. Okay, turn on. So this is on the saturation one. Be aware of that. Please note that when we want to like use those MOSFETs as a switch, we are on a saturation. Okay. Now, if both of them are triggered, A and B is equal to 1. Now we have a current passing through the circuit, so the LED would light up, so it's going to be on. If any one of those A or B the gates become 0, so we don't actually trigger any one of these two, okay, that means our circuit, the path for the current is broken, so one of them is not switched on, so there is no current conducting through the LED, so it's going to be off. And if the both of them are switched off, that means like basically we don't have again a current, so we have off. Okay, now when we have an OR signal, we use the two switches in parallel with each other. Okay, so we have the resistor, we have the LED, and they are connected to a parallel configuration of the two NMOS, and all of them are between the source and the ground. Now, in OR system, if one of the inputs is 1, the result is going to be 1. Okay, so 1 and 1 is going to be 1, meaning the LED should be on. 1 and 0 is 1, so LED should be on. 0 and 1 also 1, so the LED should be on. 0 and 0 becomes 0, so the LED should be off. Okay, now let's try. If the A is on and B is on, both of them are conducting, so we close the circuit. There is a current going through the LED, so it's on. If A is on, but B is 0, so we don't trigger B. This one is be open, but this one is closed, so we have a circuit. Okay, we have a path for the current to go from the source to ground, so still LED is going to be on. Now, the vice versa is that this one is not triggered and B is triggered, so this is cut off, but this is still conducting. Okay, so still we have a current, so still the LED is on. Now, if both of them are off, so we don't trigger either both of the MOSFETs, both of them are disconnected, so we don't have a path for the current to go through. Okay, so LED doesn't have any current, so it's going to be off. Okay, now remember, in the AND and OR, LED is in series with our MOSFET block. Okay, the logic block that we have. Now, when we talk about the NAND and NOR, which is the opposite of AND and OR, okay, now we connect the blocks of the MOSFETs are the same. So in the NAND, okay, we have the series connection of the MOSFETs, and in NOR we have the parallel connection of the MOSFET. But now, instead of using the current passing through the MOSFETs as an indicator, so it would turn on the LED, we use the voltage above this logic design, okay, as an indicator. So if the voltage is have value is not 0, then the LED would be on. Okay, now let's walk through that. Normally we have another resistor here, so we could control the current passing through the LED too. But let's do the simple one. Here, the NAND says if both of those inputs are 1, the NAND would be 0, so the LED should be off. If one of the input is on, the other one is 0, then the result would be 0, so the result would be 1, so LED should be on. If both of them are 0, the result of the NAND would be 1, so the LED should be on. Now let's look at it. If both of them are on, meaning both the transistor are conducting, okay, both sides of LED are connected to the ground. So there is no voltage across the LED, meaning there is no current passing through, so the LED is off. Now, if one of them are not triggered, that means we don't have any connection here. The connection is broken. So the LED would be connected, would create a circuit from the source to the resistor to the LED to the ground. So we have a current is going to be on. And if both of them are zero, so they are not triggered, still these two are disconnected, they are switched off. So we still have our pass for the current. So it's become again on. Now let's talk about the NOR switch. The NOR switch is in the way that if we have 1 and 1 as an input, the result would be 0, so the LED should be off. If we have 1 and 0, the result would be 0, so it should be off. If we have 0 and 1, again, the result would be 0, so it's off. If they have 0 and 0, then the result would be 1, so it should be on. Now, let's come back to the circuit. If both of them on, both switches are on, so both of them are conducting. So the voltage across the diode would be 0, ground to ground, okay, 0. There is no current conducting through the LED, so it's off. If one of them is 1, that means we still, through one of these circuits, okay, either A or B, to one of the switches, we connect the ground to the anode of our diode, okay? So still, there is no current, and it's going to be off. Now, if both of them are off, they are not triggered, that means this connection to the ground is off. So both switches are off, so we don't have any connection here. So the pass for the current would be from the source to resistance to the LED to the ground. So now we have a current, so the LED is on. So this is the way that the logic circuit, the main logic circuit, are gonna work, and we can build those logic circuit, the AND, OR, NAND, and NOR, using like two MOSFETs. In this case, we use NMOS. Okay, there are more complicated kind of like topology when they use the combination of NMOS and PMOS. Okay, or there are some other logic beside AND, OR, NAND, and NOR. All of those logic circuit also could be built with the combination of NMOS and PMOS, or on NMOS alone. So I encourage you to search on that and learn how to build other logic circuit from the MOSFETs and actually test them. Now, in our exercise, we are going to focus on AND and OR. Okay, so next step is to simulate the circuit that we have here, the topology that we have here, and see if in the multi-sim, when we simulate it, it actually would have the same result as we kind of like expect to do. Okay, so to expect to have. Okay, stay tuned. We are gonna next go to the multi-sim to see what's gonna happen in a simulation. Now, as you can see, we already kind of like put and created the schematic in our circuit, in our multi-sim. Okay, so I'm gonna just go over the schematic and try to run it. Now, we have two switches, which are our inputs, A and B, okay? And they are, each of them are triggering each switches, each MOSFET, okay? And we are using the NMOS model BS 170, okay? We have our resistor between the source and LED, and then the LED is connected in series with our resistor and our block of MOSFETs, the logic block. Okay, so this is the AND circuit. Now, let's run the circuit. Okay, where is the run? Simulate, analyze, and run. Okay, now is run. When we see both of the inputs are 0, the LED is off. Now, if I trigger one of them, That means it's 1 and 0 is still off. Now let's go for 0 and 1. And you see it's still off. So far, we're good. Now, if I put 1 and 1, you see the LED is light up. So far, our AND circuit working properly and as we expected. Now, let's go through the OR circuit. In our OR circuit, again, we put the schematic that we know. We have two switches to trigger the two MOSFETs. The MOSFETs block are connected in series with the LED and resistor connected between the ground and the source. Okay, and those two MOSFETs in the OR connection are in parallel with each other. Now, let's talk about the OR logic and see if it's working. Right now, we have a 0, 0, okay, which we expect 0 as an output, okay, and you see the LED is off. If I put the logic of input 1 and 0, we expect to have 1, which is the LED on, and we show that the LED is on. Now let's go backward. We have 0 and 1, which we still expect to have the LED turned on, and we see that it works. Now, if we have 1 and 1, okay, we still expect to have the LED turned on, and you see that it works. So we simulated that a circuit that we talked about, okay, for the AND logic and OR logic, and we see that, okay, it perfectly works. Now, feel free to implement the NAND and NOR, okay, which basically you just need to like disconnect this LED and connect it between this point and the ground. Okay, so you just need to, like, for example, let me stop the simulation. Come on. Let's stop the simulation. Now, we just disconnect the LED from the circuit, put it here. Now, the resistor is directly connected to the logic block, and our LED is connected between the point between the logic and resistor, and the other side is ground. Okay. Now let's try the NOR connection. So let's turn the rod, and you can see 1 and 1 is turned off. Now, if I turn off one of them, 1 and 0 should be 0 is still turned off. Vice versa is still turned off. Okay. Now, if I have 0 and 0, now it's turned on. So our NOR circuit is also working. Now that we are on it, let's talk about the NAND circuit. I wanted to like show you. It's not within our assignment, but oh, come on. But let's have a little bit of fun while we are here. Now let's connect these two. Connect our LED. Okay, good. Now, run. Now, you can see that the 0 and 0 should be equal to, for the NAND, is equal to 1. So it's turned on. 1 and 0 also is 1. So it's still turned on. 0 and 1 is still turned on. And if I have 0 and 0, sorry. 1 and 1 is off, yeah. And if I have 0 and 0, is also turned on. So again, our NAND circuit, the logic circuit for NAND, work properly. So this is basically the foundation of the logic circuit that are built with the MOSFETs. Okay, now stay tuned. We are gonna talk about the AND and OR circuit, and we are trying to build it in the actual lab in the on the breadboard, so we could see if the real world experimental test also is consistent with the theory that we expected and the simulation that we run. Okay.
Okay, let's talk about the AND circuit and see if it works in experimental system. Now, as you can see, I already built the AND circuit. We have the source. There is a resistor in series with the LED, and we have the AND logic block, which is two MOSFET connected in series. Okay, and I'm gonna use two jumper wire to trigger each of the gates. So we have like a switch on and off. You can use actual switches, so it's gonna be prettier. So let's try to see if it works. Now, I am gonna connect my DC source. Again, remember to connect the positive and negative polarities correctly. Now I am going to use the function generator for my triggering signal. Okay, this is no, not this one. This one. Okay, now we are good to go. Okay, before we go, let's set our function generator. I'm gonna use the square wave, but with a high duty ratio, like close to 100%. It doesn't give you the 100% as we mentioned before. So the maximum is 99.99 that the function generator can have for the duty ratio. Now, remember our voltage should be higher than the threshold voltage for the MOSFET. Okay, so to make sure, I am gonna put it in the at 4 volt. Okay, so we know we're good to go. Now, choosing the square wave, 4 volt peak to peak, and we are gonna do the offset of 2 volts because we want to start from 0 to 1, and the duty cycle would be 100%, which it do that automatically and put it in the 99.99. Okay, now we are gonna connect the output here. I am gonna turn on the circuit. Right now, both switches are off, so it's 0 and 0, which we expect the LED to not turn on. And you can see that the LED is not turned on. Now, I'm gonna connect the switch 1 to the triggering circuit. Okay, maybe I have to like. No, there is. Okay, now that we talked about the theory and we saw what happened in simulation, let's do that in the lab and put the component in a test. Now, as you can see, I already uh, built the AND logic circuit. So I have the source series with a resistor, and then it's connected to the LED, and there are two MOSFET in series and all the way to the ground. Okay, now I use another channel of my DC source for the triggering the gates, and I use this jumper wire to trigger each gate. Okay, in order to test the and table. Now let's connect the DC source to our circuit. Now, quick reminder: the MOSFETs, uh, as you know, are the metal oxide gate switches. So there is a capacitor between the gate, okay, and the semiconductor, and the other two actually terminals, the drain and source. So each time that you turn on the circuit, there is gonna be a certain level of the capacitance build up in your MOSFET. Okay, so if you do not discharge that capacitor, okay, it would affect the performance of your circuit. I'm gonna show you actually what's gonna happen. Now let's connect the second source to our circuit. This one I wanted to like use as a trigger. Now the DC, so the main DC source is set at 5, and I put the triggering, let's go a little bit lower, at like 2.3. Okay. Now, as you can see, both of my jumper cables are off. So it's the 0 and 0. Okay. Which, as we talked about, we expect that the result of the AND would be 0, which is the LED should be turned off, which you can see it's turned off. Now, if I attach one of the switches on, okay, I think my transistors are loaded. Let me discharge my transistors. Okay, I'm gonna discharge my transistors. Da, 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 da. Come on. Okay, now I am gonna put one of the triggers. You still have a capacitor, so you can see there is a little bit of light. Don't worry about that. So I am gonna change that. Oh, I made a mistake. I am supposed to discharge it with a ground. I connect the wrong port to my capacity, okay, see, I discharged the transistor and it's turned off. Now I'm gonna put one of the triggers, and please help me. Why? Okay, now it's discharged. You can see 0 and 1, it means 0, which is off. Now I'm gonna use another switch, trigger the second switch, and you can see the 1 and 0 is still off. Now I'm gonna trigger both switch. And you can see that now my LED is turned on. So the AND circuit works perfectly. Now, let's turn it off and we go to the OR circuit to show you how that works. Okay, for the OR circuit, as we mentioned before, we need to put the transistors, the MOSFETs, in parallel with each other. Okay, so that's the change that we make. Now, let's see what's gonna happen. First, we apply the signal. Okay, we from the previous test, there is a charge. Come on, in our circuit, I discharge them. Now you can see it's 0 and 0, and in 0 and 0, we expect that to be turned off. Now, if I trigger, okay, I made a little bit of mistake in my circuit. Let me fix it. Okay, that mistake was that I fully parallel those, so the gates should not be parallel with each other. So remember that. I made that mistake right now, and I fixed it properly. Okay, so good. Now I am gonna trigger one of the transistor, okay, which is, okay, my circuit is not connected. See, There is a troubleshooting going on and on. And now we are in, okay. Now our circuit is connected and I'm triggering one of the transistors. Okay, and the LED is turned on. Now I am gonna distrigger that, discharge the two transistor, which please this get discharged. Get discharged. Okay, now it's discharged. Okay, now I'm gonna trigger the other one. So it's gonna be 0 and 1. And you can see the LED is on. Okay, now I'm gonna disconnect that. Okay, this is not charged, so perfect. Now I am gonna trigger both of them. So 1 and 1, which is turned on. Now let's try again. I want to make sure that we are doing okay. So it's not the charge that makes that circuit on. See, I discharge it, but it's still turned on. So the 1 and 1 equals to 1 for the OR circuit, and we expected that to be turned on, and now we see that the LED is on. Okay, this is basically how we could build the logic circuit. You can, if you don't, if you wanted to like have fun a little bit, you can work on the NOR and NAND circuit, okay, but it's not required for our assignment. Okay, let's move on.
Okay, let's start the new conversation. And in this part, we are going to talk about the BJTs or bipolar junction transistor. They are different from the MOSFETs and basically the FET transistor. And the main difference, beside the physical structure of those components, when we talk about the application, okay, the main difference is that normally when we talk about the FET and triggering a FET, we need a voltage to trigger the gate of a FET transistor, okay? But in BJT, we are going to use current, okay, in base to trigger the transistor. Now, that being said, let's move on to the actual like discussion about the BJT, so we could like remember what's going on with this component. Now, BJT is a semiconductor device, okay, which is actually physically it's three semiconductor, either PNP or NPN, okay, which there is a three connection of collector, emitter, and base for each of those semiconductors. Now, we have two symbols. Let me clear this part. It's a little bit messy. We have two type of the BJT, as we said, PNP and NPN. Now, the symbol for BJT in electrical schematic is, as you can see, the difference between the symbol of PNP and NPN is the direction of the current. You see, PNP, we have the current from emitter to collector, and in NPN, we have collector to emitter. Now, these three terminals, as you know, we have collector, emitter, and base. We use base to trigger the BJT and let the BJT to conduct current between the collector and emitter. Okay, now what happened in a BJT is whatever current that we inject to the base, if we exceed a certain threshold, Okay. The BJT would allow the collector and emitter to conduct a current through them, okay, which is proportional, okay, which is proportional to the current injected into the base. So these two currents, the current in base and the current, we call it current of collector, it doesn't matter which type of BJT we have, these two are related to each other. So like IC is a function of IB. Now, what is that function? Is a constant proportion named beta. I don't want you to confuse that with a lot of B. Beta is the gain, is the coefficient between the base current and collector current. Okay, so current of the collector divided by the current of the base is the beta. Okay, that beta is the gain of amplification, basically, between these two currents. Normally, like for the model that we are going to use, this beta is somewhere between 100 to 300. And so that means whatever current you inject into the base, 100 times up to 300 times of that would be the current going through collector to emitter or vice versa. Now, that okay, let's start a new discussion. In this part, we are going to talk about the BJTs, which is another type of semiconductor switches. There are differences between the BJTs and the FET transistor. The physical component and the design is different. Okay, so let's talk about the BJT. Now we are going to focus on the BJT. The BJT is short for bipolar junction transistor. Okay, so we have the, you can see the symbol for the BJT here is very close to the FET, but there is a difference. There is a tiny difference between them. So make sure you don't confuse them when you read a schematic in your project. Now, this is a symbol for BJT. Now we have two types of BJT. Before we explain that, let's go to the physics of the BJT. BJT, as we said, is a semiconductor device, which is includes three semiconductors connected in series with each other. As you can see here, okay, there are three semiconductors that are connected with each other. It could be NPN, the semiconductor, or PNP. Okay, what matters is that the middle one should be different from the other two. Okay, now the two far left and far right semiconductor are connected to the terminal we call collector and the terminal we call emitter. The middle one is connected to the terminal we call base. Okay, if we trigger the base, we are going to create an electrical field here, polarize this middle one. So it would create a path for the charges to go through the semiconductor. As much as this triggering force will be higher, that means we have a higher capability of the current to conduct through the transistor. Now, let's talk about, but let's go back to the symbol. As you can see here, we have two symbols shown here, one for PNP, another one for NPN. We have collector, base, and emitter as the terminals. The difference between these two types of the BJTs, when we talk about the symbol, is the direction of the current. Here, In PNP, the current goes from emitter to collector. In NPN, goes from collector to emitter. This flash sign would show this arrow will show the direction of the current, so you can distinguish the PNP and NPN from each other by looking at the symbol in the schematic. Now, there is a very fundamental difference when we talk about the application and operation of the BJTs and FETs. In FET, when we want to trigger the switch, we apply a voltage above a certain threshold to the gate. Now, the difference between the FET and BJT is that BJT is triggered by current. FET triggered by voltage, BJT is triggered by current. So if we inject a certain amount of current above a certain threshold in the base terminal here, this switch, this BJT would allow a specific amount of current pass through the switch from collector to emitter, or vice versa. It doesn't matter between the PNP and NPN. Now, another main difference is when we work with the FET, the current passing through the MOSFETs or JFETs, whatever FET that we have, is basically mandated by the circuit. So whatever voltage and resistance, whatever happening in the circuit, that would basically decide how much current would pass through our transistor when we talk about the FET transistor. Now, BJT is not like that. The current passing through the BJT is a function of the current that we inject into the base. So it doesn't matter what are the voltages and what are the resistors or what's happening in the circuit, okay? When you inject a specific amount of current in the base, the transistor would actually define how much current is passing through that line and that switch. Okay, now what is the relation? The relation between the current in a collector, the IC, and the IB, okay, is a constant we name beta. So they are proportional to each other. Now, so as you can see, beta, which is the gain between the IB and IC, is equal to the current IC divided by the current IB, the collector current, the base current. Okay, now, so for example, if the beta is like, let's say 100, and you inject like a 1 milliamp in base, okay, the current passing through the collector, either entering the collector or exiting the collector based on the type, okay, is gonna be 100 times that 1 milliamp or 100 milliamp. It doesn't matter what type of or what value of the resistance we have or what level of the voltage source we have, the current would be defined by this function, okay, by this proportion. Now, let's move on to the voltage current characteristics of the BJT. Now, this graph defines the voltage current characteristics of a BJT. Now, the vertical axis is the collector current. The horizontal axis is the voltage between the collector and emitter. Okay, so voltage between collector and emitter, collector current. Okay, now, if you inject a certain amount of current to the base, okay, you would trigger the switch, so it would allow the current to pass through. Now, from a very tiny point, that current is a function of voltage between collector and emitter 2, but very rapidly, okay, very rapidly, it would go to the saturation mode, the saturation region, which is this part. Okay, sorry, it goes to the active region, which is this part. This part is saturation region. When the voltage of the collector and emitter is also influencing the level of the current and the amplitude of the current in collector. So this is the saturation. We normally don't work here because there is a lot of uncertainty and variation happening, and we can actually set the system as we want it. So we normally work in this part. After the current get independent of the voltage between the collector and emitter, we are entering to the active region. So this part is the active region. Now, if the current injected into the base is lower than a certain level, or as we feel like it's approximately zero, okay, we don't see any significant current in the collector. Expect a little bit of leakage in real world. So we call that region here cutoff region. So cutoff region is when we don't want to conduct current here, so the switch is off. But when we want to actually use the switch in on mode, we want to be in the active region. And as you can see, as much as you increase the IB, okay, you are going to increase the IC. We said it's proportional. Okay, now, how this graph would work for us, okay, in a circuit, either as an output, okay, as an output, the IB is input, and we are going to have an output from that BJT. Either the voltage between the collector and emitter here is our output, so we wanted a certain voltage between the collector and emitter, okay, or we wanted which is normally we don't normally care about the voltage between the collector and emitter as an output. Mostly output of our system is going to be the collector current. So we wanted to like design the collector current in a certain level that we aim. Okay, so for example, if we want to have like a alpha amp of current, okay, and we know we have like a gamma volt in our source. VCC is the voltage of the source, okay. In our circuit, we have to tune the VCE and the resistor that is series in the collector in a way that we kind of like set exactly at the point that we want for the IC in our curve. Like if we want this much of IC, okay, we need to set all the VCE and RC in a way that we land in this point. Okay, this line we call it load line or the line that defines the Q points. Q points are these points. Okay, and this is the function for this line is this equation. Okay, now this is how we work with the BJT in a circuit. We are going to talk about the IB curve of the BJT. We are going to simulate that, and we are going to test that in a lab. And we also going to see how we use the BJT, because we said the most important part is the gain, and so they are amplifiers. Okay, so we are going to see how we can use the BJTs in different configuration to create different type of amplifier in our circuit. Okay, let's move on to the simulation part of our discussion about the BJT and IV characteristic of the BJT. As you can see, I already placed the component and wired the circuit. So we have our full schematic in our multi-sim. Now in this schematic, we have two voltage source, one for creating a current, so we could inject that into the base, and you can see there is a 20-volt voltage source in series with a 1 kilo ohm resistor. So this is connected to the base. And we have another voltage source, that 50-volt voltage source, which is connected to another resistance. Here I put 10 ohm, which basically creates the voltage between the collector and emitter. Now, we want to set the IV characteristics. So I put an ammeter to measure the current of the collector. Now, if we go to the menu simulate into the analysis simulation, we wanted to like choose the DC sweep because we wanted to like sweep the DC voltage, that 20-volt DC voltage, okay, that VX, will be that V1. So we could create a certain level of the base current and see what's going to be the response of the BJT and what's going to be the collector current. Now, we also are going to change the voltage between the collector and emitter. We're going to sweep that too, okay? So we see what would be the effect of change in the voltage between the collector and emitter on our collector current. Now, let's save that simulation setting, and we wanted to like run the set. We click run, and as you can see, okay, we have we see that the IV characteristics of that BJT is same as we expect. So when we don't have any current, is zero. It doesn't matter how much voltage between the collector and emitter is. And as we inject more and more current into the base, okay, the level of the current in collector would increase. So it's a function of the base current. And as you can see, it's almost constant. Okay, there is a little bit of a slope, but we can neglect that. It's almost constant. So the V between the collector and emitter, voltage between the collector and emitter, in the active region, do not affect the level of the collector current. You can neglect this slope; it's very tiny. Okay, and in the saturation, but in saturation region here, okay, you can see that both base current and the voltage between the collector and emitter contribute to estimating the collector current. So as you can see, the characteristics, the current voltage characteristic of a BJT was as we expected in theory, so perfect. Now we are going to move on to the actual experiment, and we are going to see what's going to happen in the actual circuit. Okay, let's move on to the actual circuit. As you can see, I already built the circuit. So you are supposed to calculate the resistance that you need for connecting to the base and the resistance for the resistance is connected to to the collector. Okay, so I'm not gonna give you the values, but the whole circuit is I connected my BJT, the emitter is connected to the ground, the collector is connected to the source through a resistor,
and the base is also connected to the source, to the same source through another resistor. Now, one thing to know about the BJTs, if you look at the BJT, okay, as you can see, like the FET, there is a flat surface on one side of the BJT. Okay, now this helps you to find out which pin is emitter and which pin is a collector. Okay, now when you look at like this flat surface facing you, okay, the left pin is emitter, okay, the middle one is base, and the right one is collector. Now, this is for the model PN2222A. Now, if we have, there's another model. I mentioned that in the assignment itself with a picture. This is a NPN BJT. If we have a PNP BJT, then the collector and emitter kind of like change the place with each other. Okay, so now that we have an NPN, the model that I mentioned in the assignment, when you face the flat surface, the left pin is emitter, the middle one is always base, and the right one is collector. Now, knowing that, we connect those circuit to each other. Now, I am gonna connect my DC source. This is the negative uh, part and the positive part. Now, first, I wanted to like measure the current that is injected to my base. So to do that, I have to put the multimeter. I set it to the ammeter, and I have to connect the multimeter in series with the base resistor. Now, I am gonna connect the amp meter in series with the base resistor. Now, what I expected, as I mentioned in the assignment, we expected around 50 microamp. Okay, so we are gonna connect the probe to the socket that is good for microamp measurement, and we are gonna set our multimeter to the microamp. Again, be careful. The default is AC, so you need to change it by pushing the orange button. Change it to the DC. Now that we are okay, is this readable? Yeah. Now that we are okay, I am gonna apply my voltage. As you can see, I am applying around like 11.7 volt to my circuit. Okay, and it's a little bit. Uh, the picture is in reverse. Okay, it's the multimeter reads 50.1 microamp. Okay, so what I'm injecting into my base is 50.1 microamp. Now, let me disconnect the ammeter from the base, and I want to now measure the current in a collector. Now I am connecting the ammeter in series with the collector resistance. Okay, now this one I expect in the milliamp range, so I need to change my multimeter to the milliamp range. And again, if the default is AC, you need to change it to the DC. Okay, now let's apply the voltage. It's the same voltage that we apply, so we have the same current in a base. Now that you see, okay, I connected the probes by mistakes. No, no. This is the polarity. It doesn't matter. Here is a minus sign. Still the amp is okay. Now the ampere in the collector current, as I read, is 11.62 milliamp, which is very close to the simulation that we are gonna have. Okay, so this is how we run the test of over our BJT. Now, based on this 11.75 milliamp and that 50 microamp, now you can calculate the beta of this specific BJT. Okay, now before we leave, I wanted to like change the resistor. I use the potentiometer here. I want to change the resistor. By changing the resistor, I am changing the voltage between collector and emitter because the current is constant, should be constant. Okay, so the current is a function of uh, current in a base. So changing the resistor should not affect the current of the collector. But by changing this resistor, I am changing the voltage division between the BJT and the resistor. So meaning the voltage between the collector and emitter is changing. Now, let me change that. Now, as we change that, my if I go all the way in on my potentiometer, the current that I see is 11.1. Okay. Now, if I turn it down all the way to the other side, what I see is 11.9, let's say 12 milliamp. So 1 milliamp change. This is that slope that we see in the IV characteristics of the BJT, but it is still very little kind of like difference. Okay, when we talk about having a stability in our current. Okay, so this is basically the result that we could have. Now, if you wanted to like have the IV characteristics, okay, of your BJT, okay, in our system, you can change the voltage in a DC source, okay, and you can sweep. So that way you can change the current injected into the base. So you need several points, at least 10 points. So for example, you set the voltage in 5 volt, you read the current that are injected into the base, and then you read the current at the same voltage. You read the current that you get from the collector, okay? Then you change the resistor, use the potentiometer. You change the resistor, okay? So you can see how this current of the collector move by changing the V between the collector and emitter. Okay, so first, let's do one time for one of the curves, okay? I'm putting in the 5 volt, okay? Now, I am gonna read the current injected to the base. My current injected to the base is 20 microamp. So IB equals to 20 microamp. This is one of the curve, okay? Now that I know what is my IB, I am going to actually graph the curve for this specific IB. How we do that? We are gonna connect our ammeter. We expecting a milliamp. Be careful about that. And DC AC matters in the ammeter. Now, for this specific value, okay, my IC is 4.3 milliamp. Okay, now for this 4.3 milliamp, for that point 4.3 milliamp of IC, I need to measure the voltage across emitter and collector. So I am gonna connect these two to one to emitter, another one to collector. Millivolt. Okay, what's happening? Why is... Oh, okay, my probe is not connected. Sorry. Okay, volt. Okay, I see 1.1 volt between collector and emitter. Now, I am gonna change a little bit my potentiometer. Okay, now my voltage is 1.9. Okay, for this specific point, I need to again read uh, 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 read the IC. Something is not right. Oh, okay. Let me see what went wrong here. Da, 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 da. Oh, sorry. See? AC/DC. So for that specific uh okay, now let's move on to the actual experiment to see what are gonna be the IV curve and the beta measurement for our BJT. Now, as you can see, I already created the circuit. So I have a voltage source which is connected in series to the transistor, to the BJT, using a resistor. And also I connected the same voltage source through another resistor to the base terminal of my transistor. Now, the transistor that we use is the model PN2222A, which is an NPN transistor. Okay, now how to know the pins in this model? There is a flat surface similar to the MOSFET that we saw before. There is a flat surface in the component, the BJT. If the flat surface faces you, okay, if the flat surface faces you, the left pin is going to be emitter, the right pin is going to be collector, and the middle one is always base. Okay, now if you have the model P2N22A, which is the other type of the BJT, now the collector and emitter replace places. Okay, change their place with each other. So in this model that we use, the face this flat surface, the left one is emitter, the right one is collector, and the middle one is the base. Now, let's move on to our circuit. Now, the two resistors that we use in the circuit, I ask you to design the value of those resistor by yourself. So I'm not gonna give you the values for the resistor. Okay. Now we ask for somewhere the between 50 to 60 microamp of current injected into the base. So I am gonna connect my voltage source, and I want to measure the current that is applied to my base. So I make sure that I actually have that amount of current. Okay. Now I expecting a microamp, so I'm gonna put the probe on the microamp socket, and I'm gonna set that multimeter to the microamp. Again, the default is AC, so you need to change it to the DC. Now is microamp DC. Okay. Now I am gonna turn on my circuit. Okay. I applying 12 volt in my source, and my meter reads 51.4 microamp, which is injected into my base. Now that I know what is my base current, I want to see what is my beta. So I want to check my collector current. So using the formula that we mentioned before, we could calculate the beta. Okay. Now I am gonna apply my I'm gonna connect my amp meter in series with the other resistor, which is connected to the collector. Now I am expecting a little bit like around like a milliamp range, so I have to like change the multimeter to milliamp. Again, the default is AC. You need to change it to the DC. Now we changed it. We are gonna apply the voltage. Okay. My multimeter reads 12.3 milliamp. Okay, so it's 12.3 milliamp. So based on that value and the 51 microamp current in a base, I can now calculate the beta for this specific BJT. Okay, now this is for calculating the beta. How we can actually graph the IV curve based on measurement. Now, this is a little bit harder than the FET, so we need to have more work actually to do that. Now, let's put the connection back. And first, if you remember the curves in the BJT IV characteristic, the vertical axis was IC current. The horizontal one was the voltage between collector and emitter. So these two are the main measurement that we have to do. But to graph each of those curves, we need to first set the I of base, the current of base, to a certain value. And on that specific value, now we measure the IC current and the voltage for the different voltage between the collector and emitter. Now, so we need to set the current of emitter microamp DC. We are gonna go down. We want to like check some of the voltage, so we want to like have multiple measurement point. So right now I'm putting in a 3 volt, and what I see is 10.9 microamp of base current. Okay, now we're good. We are gonna for this specific base current, we are gonna read the current in collector. Current in collector, which is milliamp DC, remember. Now, in this specific setting, my reading is 2.4 milliamp. So the first thing that you need to write down is 2.4 milliamp of current in a collector, okay, for the first set of measurement. Now, what is the second part of the first set of measurement is the voltage between collector and emitter. Now, to do that, with the same setting, nothing is changed. I am gonna put that into the voltmeter, and I am gonna connect the probes between the emitter and the collector. Okay, and I'm gonna apply the value. Now, what I read is 3 volt across the collector and emitter. Now, so this is the first vector, the first point in your graph on one of the curves. Okay, so the curve for that specific 10 micro amp of base current, the first point on that curve is we measured already the 4 milliamp, around 4 milliamp. I don't remember. But check the video. Go back and check the video. And for that 4 milliamp, on that curve, it happened on the VCE 3 volt. Now, we are gonna change the voltage. How we gonna change the voltage? By changing the potentiomet that we use as a resistor in series with the collector. Now, we know that the current in a collector is a function of, ideally, a function of the current in a base. So no matter what type of resistance is here, that current would not change. So what would change this resistance? The voltage division between the transistor and the potentiometer. So if we change the potentiometer, we're basically changing VCE. Now I am gonna change the potentiometer. So now I am on 2.9 volt. Okay. Now for this specific volt, I am gonna measure the come on, don't get disrupted. Okay. I am gonna measure the collector current. That was a milliamp. Remember, it should be DC. Apply the voltage. It is 2.4 milliamp. So this is the second set of my measurement. Are we good? Now, again, I am gonna change the potentiometer. Now I have 2.4. Let me change it a little bit more. Now I have 2.39 milliamp of the collector current. And I am gonna measure the voltage between the emitter and collector again. Now I have 2 volt across collector and emitter. So this is the third set of my data. Now you need to have like at least 10 point for the data. So now you have the curve for that 10 microamp base current. Okay. After that, you would change the voltage source. That way, you have another base current, and you repeat the whole process. Now you have your second curve in the IV characteristics, and again the third curve. It is a little bit time consuming and energy consuming, but this is the way that you can actually create that IV characteristics based on the measurement. Okay, let's move on to the next.
Okay. In this part, we are gonna talk about the Class A amplifier. First, we are gonna talk about the some of the characteristics, and then we are gonna go over the schematic of the Class A amplifier. Talk about some of the characteristics or like the parameters that we use for like a rule of thumb to design this, and at the end we are gonna actually design a specific amplifier, which we are going to also test it in the lab to see if our design is matched with the actual measurement and result. Now, first, Class A amplifier, or the basic amplifier that you can make with the BJT. Now, some of the characteristics that they are inverting amplifier. What that means whatever input that you have, okay, the output is gonna be 180 degrees shifted. So the positive half cycle become negative half cycle become positive half cycle. Okay, so you have half cycle shift in your AC signal. Now, these amplifiers have a very good linearity. Okay, but what is missing is that they have a very poor efficiency. Actually, the worst type of amplifier when it comes to the efficiency. The theoretical maximum efficiency that you can get from the Class A amplifier is 25%, which we never even get close to that. Normally, is the practical one is like have an efficiency of like around 14%. Okay, so efficiency wise, this is a very poor and actually the worst structure of the amplifier. Now, the schematic of the amplifier, okay, is as you can see here, we have a BJT, okay, which works through the full cycle. So it is on through the 360 degree of an AC cycle, okay. We have a resistance attached to the collector and a resistance attached to the emitter, okay? And then we have a voltage divider to bias our base, okay? And then we have input and output. Now, you can see some capacitors. Actually, there is another capacitor here also. C, let's go E, C2, and C1. Now, the reason that we use C1 and C2 is to filter out the DC aspect, a DC component of the input. Okay, so we have a pure AC going into the base, and then the output we also filter out the DC component that for whatever reason could be injected to the signal because of our amplifier. Okay, so we could filter that out and we have a pure AC at output too. Okay, now why we need RE? If you don't have an RE, what you see, what the resistance that BJT sees toward the emitter, okay, can be defined based on the voltage across this line, across the emitter, okay? And this is the voltage of the BJT, this is the physical characteristic of the BJT, divided by the current that's passing through that emitter, okay? Now, this RE become the voltage, it is characteristic voltage, which we call it thermal voltage, Okay, and it's constant. Normally, it's constant for each individual one, and it's around 25 millivolts. Okay, so this one is around 25 millivolts, and at the denominator you can see IE. This is the Ohm law. Okay, IE that could define the RE. Now, normally because it's millivolt and IE also around millivolt, what we have is a very low, like in a scale of less than a 10 ohm of RE. Now, RE, as we said, is based on the VT, which is a characteristics of the physical characteristics of the BJT. Now, each individual model of BJT could vary, the VT could vary between those models, and even in one model, when you have like a several BJT that are all of them are have the same model, okay, still we have a variation in thermal voltage. Beside that, so it's uncertain. Beside that, this is actually it's on the name, thermal voltage. If we have a rise in the temperature of our environment or BJT, that would change, and we don't have much of a control over it. Okay, so the variation in VT could affect our resistance here. Now, what we do is we want to basically dominate the resistance in a way that we actually make the effect of this RE very low, so the variation on that RE would not actually affect significantly our result. Now, to do that, we are adding this capital RE resistance on the emitter, which is much higher than this one. Okay, so it would dominate the whole resistant part, so it would cancel out this variation effect. Okay, now, what is this CE here? We have an AC input in our base, and we know that the current of emitter is the current of collector plus current of base. Now, you can consider current of a collector as like DC. There is a very, very, very low, close to zero AC part, but I base, the current of the base, we actually input an AC signal. So we can neglect that. So there is an AC component here. Okay? Therefore, we have an AC component in the emitter current. Now, when we wanted to like set our BJT, we set it based on the DC component. We bias the whole thing based on the DC component. So any AC component in the resistor, in the RE here, would affect the voltage biasing, the voltage across the emitter, the voltage of the emitter, the voltage of collector emitter, okay, and the voltage of base. Okay, so it would disrupt the whole design. Now, what we do is we use a bypass capacitor here to drain all the AC component in the IE current, okay, in the current of emitter. So this one in the AC mode, it would short circuit the AC, so the AC would not go through the RE. So we have a stable voltage at our emitter, which is only like the DC component. So it swallow all the AC part that gets the emitter. Now, this is the whole idea of the design of a Class A amplifier. Now, this R1 on R2, we already talked about that we need to bias our BJT. So one of the method that we could use a bias is a voltage divider. Okay, so in this specification, you can use different type of like biasing method here. This circuit that we wrote here, that we draw here, has a voltage divider biasing. These R1 and R2 that actually are voltage divider that help us to bias the base. Okay, and the whole BJT basically. Now, let's remind us about some of the equation and some of the component that we know about the BJT. We know BJT has a beta coefficient, Greek letter beta, which is the ratio of collector current to the base current. This is one characteristic of a BJT. You can find in some datasheet, this beta is referred to HFE. Okay, so do not kind of like get confused. This is the same as beta. Okay, now we know that the voltage between base and emitter is normally close to 0.7. And if we bias the BJT properly, which is what we want to have, it won't change. So it's 0.7 volt between base and emitter, and this is collector. Now, when we talk about the gain of class A amplifier, okay, the gain of class A amplifier is equal to the minus collector resistance over emitter resistance. Collector resistance over emitter, and this minus is because of that inverting effect that we talked about. Okay, we talked already about this lowercase RE, which is the intrinsic resistance of the BJT. And we already know that the IE, the current in emitter, is the summation of the current of the collector and the base, which since the collector of the base, the collector of the current of the collector is beta time collector of the base, and it's normally somewhere between 100 to 300. So current of the bases are significantly lower than the collector current. So we can actually consider the emitter current equal to collector current. Okay, now this is the discussion, theoretical discussion that we need for our class A amplifier. Now let's try to go over an actual design for a specific requirement. Now, you can have different requirements when you want to like design. Sometimes you want a specific voltage at the output, or sometimes you wanted to have like a specific impedance watching the whole system from the output. This is the impedance is for sometimes that you wanted to like do the impedance matching for maximum power transfer. Okay, so sometimes, as I said, this is the output impedance that matters. Okay, sometimes you need a gain to be a specific value. Okay, now we are going to talk about a specific example of our design. Now, for a specific for this characteristic that I wanted to like consider is, first of all, let me use another color. First of all, I wanted to like see what is my DC voltage source. I'm going to define in this specific design that my DC source is 9 volts. Okay, what you see in the assignment is different. So you wanted to like use this type of calculation to design your own kind of like class A amplifier in the assignment. Now, I want to have the collector current equal to 10 milliamp, and I want to have a gain close to 5, actually minus 5. Okay, now let's see what we can do. Now, the rule of thumb for voltage of the emitter, the rule of thumb for designing the BJT and biasing the BJT is that we want the voltage between the collector and emitter be in the middle of the whole voltage of BCC. Why is that? You remember in a characteristic curve that we have for the BJT, we talked about the load function, the Q points. Okay, in order to have a quiet, stable, and a wiggle room in our system, we want to put the Q point at the middle of our characteristics. That means we want to have the voltage between collector and emitter equal to half of VCC, which is 4.5 volt. Okay, now this is the gain that we want, so it's 5, and we know that the gain is RC over RE. Remember, we consider the collector current and the emitter current and collector current equal to each other. What that means? That means through the Ohm's law, this AB is also the voltage across the RC over the voltage across the RE. Okay, now we have 4.5 across our collector. That means these two voltage RC plus voltage RE are also 4.5. This is a KVL. Okay, now this one is supposed to be 5 times bigger than this one. Neglect this minus part. This minus part is for AC. We wanted to like do the amplitude. Okay, so it's 5 times this one. So this is become, so the 6 times 5 times RE plus voltage of RE plus voltage of RE is 4.9, meaning that the 6 times voltage RE is 4.5. Therefore, voltage RE is 4.5 over 6, okay, which is, let me calculate that using a calculator. I'm not feeling to do that on my head, okay, so 4.56 become 0.75 volt. So this is our emitter voltage. Now that we have our emitter voltage, let me erase these functions, these hints and equations. I need some space. Now that I have the voltage of the emitter, okay, this is the voltage across RE. So I can see that RE is that voltage over the collector current, which means 0.75 over our collector current was 10 milli amp. Okay, so what's happening is that it's become, this is a K, so it's become 0.7 K, which is 750 divided by 10, so RE is 75 volt. Now, the voltage across RC is 5 times of that. So it's going to be voltage across RC is 5 times 0.75, which is 25, and this is 35, so it's become 3.75 volt. Okay, now we have I think it's a little bit out of the picture, so 3.75 volt. Now it's better. Now, so again, we have the collector current, so RC becomes 3.75 over that 10 milliamp, okay, which basically means 375 volt. Now we have our RC 375, our RE is 75. Okay, now did I do the calculation properly? Let me check that. I think, okay, 5 times 0.75 Yeah, it's correct. Okay. Now, so far we have RE and RC. Now we need these two resistors. Okay, so let me erase again. So we have enough space. How we could do that? Now, we said voltage between base and emitter is always 0.7. So this is because we want to have like a perfect bias, a stable bias. So what it means is that the voltage of the base voltage here, okay, is gonna be 0.7 plus whatever voltage of emitter is, which is in our case the voltage of the emitter was 0.75. So this become 1.45 volt. Correct? Yeah. This is gonna be our base voltage. Now, what is our base current? Our base current is the collector current over that beta. We consider our beta as equal, let's consider our beta, okay, as 100. For easy, it's not going to be exactly as 100. Okay, so you are going to see in the experiment that it is going to be different than this number, but let's go for the 100. Okay, it's not going to change affect significantly. So this one become 10 milliamp over 100. Okay, which means it's 0.1 milliamp over 100 micron. Okay, so this is our base current. Okay, now in order to have a perfect biasing, okay, we want, this is the IB, we want that IR2, okay, we want that IR2 is significantly bigger than I of the base. So the rule of thumb is that we want IRE to be at least 10 times of IB. Okay, what that means? That means our desired I1, why I1, R1. No, this is 2, sorry. So our desired R2, current of R2 is 10 times 0.1 milliamp, which is 1 milliamp. Now, this is 1 milliamp, and the voltage across it is 1.45. Okay, so that means that our R1 is 1.45 volt over 1 milliamp, which if you do that is become 1.45 kilo ohm. Now we have our R1. So this one become 1.45 kilo. Now the remaining part is this is R2. Yeah, why? Okay, R2. Now the remaining part is only R1. Let's do that. Now there is two way to calculate the R1. One is to use the voltage dividing rule. Okay, we have a VCC, and the divider gets to have like make us to have like a 1.45 of volt across R2. So using the formula for voltage divider, which is, if you remember, like the voltage across R2 is gonna be the VCC times R2 over R2 plus R1. So using this, we have this one, we have this one, we have this one, we have this one. So we solve for R1. This is one way. Another way is to use KCL. So I of R2, we have that, and we have IB. So if you run a KCL here, that means the I of R1 should be the summation of these two. So IR1 is IR2 plus IB, but we design IR2 as 10 times of IB. So it's become 11 times of IB. Okay, so basically IR1 becomes 1.1 milliamp. Okay, now in order to calculate the R1, we need the voltage across it too, but it's easy because the voltage here in base is 1.45 and the whole voltage is 9 volts. So the voltage across R1 become 9 minus 1.45, which is 7.55 volt. Now we have these voltage and current. That means we can calculate R1, which is 7.55 over 1.1 milliamp, which is, I'm gonna use the calculator, 7.55 divided by 1.1, oh, 1.1 milliamp. Let me. Come on. Which become 6.8, around 6.8 kilo. Okay, so now we have this one, which is 6.8 kilo. Okay, now we have everything in our circuit. Now what we have to do is to implement that. So based on the whole circuit, we have to have a gain of 5 and the collector current of 10 milliamp when we have the voltage of VCC. Now, before we go that, let's actually run a small signal analysis for our circuit. This is actually gonna be very helpful to understand what we actually see, because all these calculations that we did, there is no input circuit here, there is no input, and there is no load or output here. So when we add those things, what is gonna happen is that we're gonna see different gain because it's changed the circuit. Now, how we can actually model our amplifier? Okay, what we have, we are gonna see an input impedance between the input and the ground. Okay, this is Z in, and then we are gonna have a dependent voltage. Okay, and the output impedance, Z out, and this one is gonna be, we know that the gain is 5, so it's gonna be 5 times the V of in. This is the V of in, okay? V of input, okay? So let's see what's gonna happen now. For this one, okay, we need input impedance and output impedance. Output impedance is easy. Output impedance is gonna be equal to RC. So our output impedance is 3750. Now, input impedance needs calculation. To do that, you need to have like a Thevenin equivalent looking from the input. So if you remember, for the Thevenin equivalent, we have to like short circuit the voltage sources and open circuit the current sources. Now we have one voltage source. So if we short circuit that, that means here also we have a ground. So if you watch to the circuit, then that means if we ground that, that means we have R1, which is between the input and the ground, R2 between input and the ground, and here RE between input and ground, but this is not RE. We have a BJT in the middle. We have to transfer the RE to the base. So these are the parallel resistance that creates that input impedance. Now, how we can transfer this one? When you look at this circuit, we said that the IE is IC plus IB, but IC is beta times IB, so it's become beta plus 1 times IB. If the current here is beta plus 1 IB, that means the resistor that we see from the base is going to be that equivalent resistor is going to be also beta plus 1 times RE. Think about that, okay? Do the Ohm law and think about that, okay? You can do another Thevenin only for the BJT and RE, and you can find this is true. So that R equivalent, in our case, this beta is 100, so it becomes 101 times RE. So now, this resistance, R2 and RE are parallel with each other. So you can calculate the input impedance, the Z of input will be equal to R1, parallel with R2, parallel with R equivalent. Now, it's not easy to calculate. I'm going to pause and come back. I'm going to calculate that and come back for the rest of the analysis. Now, if you do the calculation for that Z in for the parallel R1, R2, and RQ, do the calculation yourself, but Z in is going to be 1.03 kilo. So here, we are going to have 1.3 kilo. Now, let's connect a signal generator. We have a signal generator. We are going to input like 3 volt, let's say 3 volt, peak to peak. Okay. And we consider that our signal generator has 50 ohm of internal resistance, which is normal. Okay. Now we are going to add a load of 1K at our output. Now let's see what's going to happen in our system. Now we have 3 volts. The voltage in is going to be divided voltage, so the between the 50 ohm and that 1 kilo. So what's going to happen is that the voltage in is going to be 1030, 1.03 kilo over that 1.3 kilo plus that 50, which is 1.80 times the whole voltage, which is 3. Okay. Now, if you do that calculation, since the input voltage is not the input impedance, that generator impedance is very lower than this, we don't expect a lot of like deviation or from the voltage in our input. 3 is going to be 2.86. So our input voltage is 2.2. Sorry. 2.86 volt. Now, so here is 2.86. Now, 5 times of that is going to be this voltage source. So I'm going to erase here. So the voltage here is going to be, let's say, V1. The V1 is going to be 5 times 2.86, which is, let me calculate that, 5 times 2.86, which is 14.3 volts. Okay? 14.3 volts. Now, 14.3 volts is across these two. So now V of output is again the divided voltage between that Z out and that load. Now, again, so V out is gonna be 1 kilo ohm over the summation, which is 1375 ohm, okay, times that voltage, which is 14.3. Now, therefore, V of out become, let me calculate that, 1000 over 1375 times 14.3 is 10.4. 10.4. Now, see, what would be our gain? We have 10.4 in our output, and we have 2.86 in our input. So our gain would be 10.4 over 2.86. Let's calculate that. The actual gain is going to be, 10.4 divided by 2.86, which is 3.63. Okay, now look at what happened. When we designed the whole thing for A, the theoretical A that we designed it was AV was -5. Let's only talk about the amplitude. So amplitude of the AV was 5. But when we design the whole system and we add a specific input and a load here, we see that now our gain is deviated and we can get 3.63 gain as a gain of our circuit. So this is basically how the Class A works, how we can design the Class A amplifier. And after that, you can actually evaluate what's going to happen in actual situation if you know your load and your input. Okay, now, as I said, there should be, like in our case, we consider that the gain, the collector current, and the VCC is our input for the design. Okay, sometimes you need like impedance matching. Okay, so you need that Z out to be equal to your load. So that way, you have to start with Z out. What that means? That means Z out is RC. So, for example, if we need 1K as our load, and we want impedance matching, so our RC would become 1K. Okay, and therefore we know that what we want from VCE, okay, and the current going through the RC and the voltage across RE and the current going through the RE all together, we would help you for those formula to calculate one by one for these resistors, okay, and see what's going to happen. Now, we didn't calculate the capacitance here. These capacitance are used for, as we said, blocking the DC. For this specific assignment that you have, you just can pick a large number capacitance, okay, and put it in your C1 and C2. You don't need to actually do the bypass. If you like, you can do that. But what you use to actually calculate the value of C1 and C2 is to use the bandwidth that you want, okay, and the bandwidth is the range of the frequencies, okay, that you want to work in input and output. So the bandwidth and that you want, and you calculate the C1 based on the cutout frequency of that filter that we designed. Okay, same goes for the C2 and CE is also a bypass, so you can use again the cutoff frequency for a RC filter here to calculate those C1, C2, and CE. Since we are gonna have like a filter design later on, I'm not gonna go over that, and you don't need to like calculate those, but is a hint. You can use those theory if you want to like actually implement a precise capacitance in your current assignment. That's it. Let's go to the lab and see if we actually did a good job and we can have such a gain in our system.
Okay, guys. The same circuit that we designed in our previous part, I implemented the same circuit here. Okay, and I'm gonna input 3 volt of a 1 kHz sinusoidal, as you can see here, and I'm gonna see what's gonna be the output of that signal. My channel 1, which is the yellow signal, is going to be our input, and the channel 2, which is the blue one, is going to be our output. Now, let's start the system, and I set the VCC at 9 volt. Okay, and now I'm going to input my signal. Now, you see, based on, let me do a little bit better. Based on my measurement in our oscilloscope, my input voltage is 1.5 a square in my grid, and the voltage division for my channel 1 is 2 volt. So basically, that means I have like a 3 volt of voltage peak to peak for my input. Now, as you can see, my output, which is a little bit shifted, is not perfectly 180 phase shifted, but it is shifted, okay, based on my input. This is one square, 1 unit of our grid in my oscilloscope, and my voltage division for the channel 2 is 10 volt. So what happens is that my output is going to be 10 volt and my input is 3 volt. So let's divide those. So I have 3.33 gain, which based on, and the load, my load is also 1K. Okay, and my source is 3 ohm, and the inside impedance of that voltage signal generator, the signal generator, is 50 ohm. So it's the same as what we done with our actually the same situation that we done for our small signal analysis at the end of last part. So we saw that based on that values, okay, my gain, my theoretical gain should be 3.63. What I actually have is 3.33, which is very close, and that difference is, as you know, because of the errors that we have in the resistance. But the main source is that we considered our beta as equal to 100, which we know is not going to be exactly 100. So I didn't calculate what is the beta is, but you can use the previous task that we have in our assignment to actually calculate the beta of the BJT that you are using for your class A amplifier. Okay, so you know what is the difference, and even like if you wanted to like use that exact beta in your calculation, that's gonna be perfect. So this is basically how the class A amplifier would work. Now, next we are gonna talk about the class B amplifier.
Okay, let's talk about another class of amplifier, which is class B. In class B, we have two BJT. One is NPN, another one is PNP. They are collected in a back-to-back situation. And what's going to happen is that in this class, actually each of those BJT are going to be on for half a cycle of input. So when you have an input, okay, for the positive half, the voltage across base emitter here is going to be exceeding the threshold. So we have positive voltage here, negative voltage here. Okay, so this one is going to be off, this one is going to be on. So we are going to have a positive half cycle going through Q1, and a negative half cycle is in reverse. This one is going to be a negative voltage. This one is going to be a positive voltage. So we are going to have the negative half cycle through the Q2, and the rest. Then the output is going to be pure, not pure, but the whole cycle. Okay, now what is important in this class is that it is efficiency-wise better than the class A. Normally, the efficiency, the max efficiency for class B is around 78%, which is significantly higher than 25% for the class A. But the problem with that, this type of amplifier is that one, when we have a common emitter class B amplifier, the maximum gain we can get is 1. Okay, so this is one limitation. Another limitation is that consider this voltage. Okay, we know that any specific plus voltage here would not turn on the Q1. So we need to have like a threshold, which is 0.7 volt. Okay, so until the positive half cycle reaches the 0.7 volt, in this area and this area, the Q1 is still going to be off. So what we're going to see is not a perfect positive cycle. So we are going to see turn off. And then when we exceeding that 0.7 volt, we are going to have like a conduction. And then again, after it's fall below 0.7 volts, we have a off situation. Same goes for the Q2. So we have a little bit of off situation, and then even we exceed the 0.7 volt, we are gonna conduct, and then when we fall short, we are gonna have an off situation for the Q2. So what's happening here is that, as you can see, we are gonna have a distorted signal at our output. Okay. Now, what is distortion? What is the duration of this distortion? This is going to be -7. This is 0.7 volt. This is going to be minus 0.7 volt. Now, this time, let me show you with another color. This time is going to be the distortion, the off time between positive half cycle and negative half cycle. Okay, that we need to pay attention to that off sign. Now, you can calculate that because you have a sinusoidal signal that you know the voltage of the peak. Okay, so you can calculate what is the angle. What is the angle here? Okay, the theta is here, and that theta is gonna be the theta here. The difference between the 180 and this theta is gonna be a certain omega t, like omega t1. Same goes for that theta. So we are gonna have omega t2. And now you can have your T1 and T2, and the delta would be basically T2 minus T1. So this is going to be our delta T, or the duration of the T. So it's going to be sine inverse of these values. So you have time and you have the, excuse me, and the values of theta. This is how we can calculate that. But we don't normally calculate that because we can measure it very easily. Okay, so if you see that voltage, that signal in an oscilloscope, you can use the units and the time division in the oscilloscope and easily see what is going to be the difference, these off period in your signal. Now, another aspect that is very important in the Class B amplifier is the efficiency. Now, we know that we actually define the efficiency as the output power divided by the input power. But what is the output power? Output power is what we get at the output over the load. So we have a load. Okay, whatever power we have here, which means the voltage against the load times the current, so P out. Let me be a little bit here. P out is going to be the voltage of the load times the current of the load, and the P in is whatever power that our VCC, our source, DC source, is going to inject to the system. Okay, now the input power is VCC times the current of the source. But when you look at this circuit, the current that source inject here has two terms, is the summation of two terms. One current is the current that we get for biasing the base, and another current is based on the current AC, but since there is off time in each of these Qs, in each of the switches, so we need to calculate the average of IC. So we have the values of average and we have the VCC, so we can calculate the input power. Now, normally these R1 and R3 and R2 is relatively smaller than these two, but R1 and R3 are very big, okay, compared to the rest of the circuit. So that biasing current, you can consider it approximately to zero when you relatively to this IC average. So this IC average is much higher than this IB biasing. Okay, so you can neglect that. Basically, it won't change much in your calculation. So basically, when we see that, that means our ICC, the current injected by the DC source, is basically equal to, or approximately equal to, the collector current, the average of the collector current. Now, how you can calculate the average? We have to calculate the P in and P out to be able to calculate the efficiency. And this is times 100 because we wanted to represent it as a percentage. We said P out is the power of the load. So it's going to be the voltage across the load times the current across the load. If you do the Ohm law, that means it is going to be the voltage across the load square over the load. Okay, now that means if you want to simplify that, it's going to be V out square 2. This V out is divided by the square root of 2 because we wanted to calculate the RMS. Okay, so it's going to be 2 RM. So this is going to be our P out. Now, what is the voltage out? We said that the value here, okay, the value here for the gain for the common emitter class B is around 1. So whatever voltage you have here, you can approximate the output voltage equal to that. Okay. Now, so it is gonna be equal to or approximately equal to input voltage. Okay. Now, for P in, we said is gonna be VCC times ICC, which is ICC is average of the collector current. So is the half cycle rectifying system situation. So the average of this collective current is gonna be peak of IC over pi. Okay, so you can calculate what's going to happen to the what is the average of collector current, and you put it into your system, and you know the VCC, you can calculate the output, the input power, and when you have the output and input, you can calculate the efficiency. Now, let's walk through an example for how we could calculate and actually calculate the efficiency of an example of the circuit, okay? Okay, let's calculate the efficiency of a specific example. Let me eliminate some of these unnecessary values. Okay, this is going to be okay. Let me put that as square again. Okay, we are going to talk about a specific circuit when our VCC is like 8 volt. Okay, and our input voltage has a 3 volt of peak. Okay, so it's 3 volt peak, meaning 6 volt peak to peak. Okay, now 3 volt peak. Now, and our RL, let's consider it 10. Okay, now what's going to happen? We said that our P out is V out divided by square root of 2, all of that is square over RL. Now, we have a common emitter class B, so our V out is equal to V in, so it's gonna be 3 volt, okay, squared over 2, and our RL is 10 ohm times 10 ohm, okay? So this is gonna be our P out. So if we calculate that, is gonna be 9 over 20, which is 4.5, so it's 0.45 watts. Okay, so this is our P out. Now our P in, let me use another color. Our P in is VCC times ICC. We said ICC is equal to the IC average. Now, what is IC average? The peak of IC, we said the IC average is IC peak over the pi, right? Now, what is IC peak? Is the current that goes through the circuit. So it is going to be the same current that we have through the RL. So if our peak voltage is going to be 3 volt, okay, then our ICP, not here, then our ICP is going to be that 3 volt over 10 ohm, which is 0.3 amp. Okay, now this is ICP, so our IC average is going to be that divided by pi. Let me calculate that. So it's going to be 0.3 divided by pi, which is around 0.095 amp. This is our average. Now, VCC is 8, so it's going to be 8 times that value, which is 0.095 7.76. Okay, so this is our input. Now, what would be our efficiency? Output divided by input, which is 45 over, this is 0, 76 times 100%. So if you calculate that, we can see that, let me calculate that. So it's 45.45 over 0.76, which is 59%. So this is our efficiency, which is quite lower than the maximum. Okay, but this is for this specific circuit. Okay, now this is how we could calculate the efficiency of a class B amplifier. But one of the most important part to know about class B is that off time, is that distortion. Okay, so you need to also measure how much distortion you have, meaning you have to calculate that time interval, the length of that time interval, and measure that. Actually, you don't need to calculate that for this assignment. Measure that time interval, so you could have the sense of how much distortion you would have in your class B circuit. Thank you, and let's go to the lab to see if we actually can, how we can measure that distortion, and if we can actually confirm that our efficiency is as we calculated.
Okay. So far we talked about the class AB amplifier. I built up the class AB amplifier that we talked about earlier in the previous part. Now I'm measuring the input and the output. The yellow signal is the input and the blue signal is the output. They are kind of like, because the impedance of the signal generator is like around 50 ohm. So the amplifier is dominating the situation. You can see that even that distortion caused by the Class B amplifier also influence the output of our signal generator. Now, let's see about the distortion that we talked about. In simulation, you can create a very clear waveform, so it's easier to calculate the distortion signal. But here we also can see, we can't see exactly the distortion equal to 0, but you can see that the distortion happening here at this area. So we have a pure sine. This double vision is because of the noises that I have. So I didn't have any capacitor or any filter in my circuit. So this is because of the noise. So ignore that. So this one is the main waveform, and you can see the distortion part here. It takes 1 unit of my oscilloscope grid during the time. You can see that, but it's 1 unit, okay? And my time division is 50 microsecond. So my distortion duration, my time distortion duration here for this specific circuit, 9 volt of the voltage source and 3 volt of 1 kilohertz sinusoidal signal is 50 microsecond in my output waveform. So, and my load is 1K. Okay, so my load is 1K. So this is how we can measure the distortion, the time duration of the distortion in our circuit. Now you might feel or see less noise in your circuit because my setup is too jam-packed and is in my office, there is a lot of like other equipment that could interfere with the circuit. So hopefully you would have a better curve, but eventually it's not gonna be different. So you can see the distortion in the waveform, and you can measure the duration of that using the oscilloscope. And that's about it. Thank you.
Okay, now that we so far covered class A and class B, let's talk about the class AB, which is developed to address that distortion that we talked about. So before we said that the class B would have a distortion in the voltage, that crossover distortion, zero crossing distortion, and we wanted to like solve that. And we said this is actually because of that 0.7 volt that we need here and here in order to turn on the transistor. Now, in order to solve that, we need to provide to kind of like shift the input data here in the two base 0.7 volt. So any input signal could immediately trigger the BJTs on. So what we are going to do to do that is we are going to get rid of this resistor, okay? And instead, we are going to attach two diodes between the two bases. Now, when you apply, excuse me, when you apply the signal, this we know that these are silicon diodes. The voltage across a silicon diode is always 0.7, around 0.7, yeah, basically around 0.7. Okay, so this basically at a plus 0.7 in a positive half cycle to the voltage of the base and emitter here, and minus half 7 to the voltage of the base and emitter here. So now in a positive half cycle, okay, because we meet the required threshold voltage with this diode, now our signal is gonna go through the amplifier without any zero crossing distortion, and same as negative half cycle. Now, this is theory. We know that we approximately say the voltage drop against the diode across the diode is 0.7, and the voltage between base and emitter in an active region we call it 0.7, but both of them are approximation. Okay, so they are gonna, in reality, we don't have exactly 0.7 in each of these. Okay, so that means there are gonna be some distortion still existing in our waveform. So, but it's gonna be much less than what we had in the class B. Now, let's add these two diodes in our circuit, in our class B circuit, okay, and see how it would improve the crossing zero distortion that we saw in a previous test.
Okay. In this circuit, I added the two diodes between the two bases, and I'm gonna apply the same voltage that I applied in the previous test. And I didn't change anything in the circuit beside those adding those two diodes. And I'm gonna apply the voltage and apply the input. And now you can see, let me zoom in a little bit. I still have that noise. Is not because of the circuit, it's because of the environment. Okay. But you can see that now I don't have, I hope you can realize that. If you see the signal, you can see that the zero crossover, uh, the rising one is the actual signal. The other one is the noise and the reflections. So this one, you can see in the zero crossing part, now I have very small even I can see that right now in a 20 microsecond time division. Even if I zoom in, you can see there is very, very tiny distortion that even I cannot detect, the oscilloscope cannot detect. Okay, so you see that this diode perfectly, actually, this is the output, perfectly covers and improve that zero crossing distortion in the class B amplifier. So this is quite experiment that you are expected to do in second lab assignment.